In the quiet darkness of the cosmos, there exist corpses of suns, remnants of once blazing giants, now compressed into spheres, no wider than a single city. Yet, within their silence, lies a weight so unbearable that 1 teaspoon of their matter outweighs mountains, continents, even nations combined. These are neutron stars, tombstones of stellar life, carved not in stone, but in collapsed atoms. Here, in this crushing stillness, the familiar scaffolding of nature shatters. Atoms, the very architecture of matter, are stripped of identity. Electrons are driven into protons, neutrons pressed shoulder to shoulder until the boundaries of individuality dissolve. It is a place where matter is transformed into something the universe never intended to be, something that defies imagination and resists language. Around them stretches the infinite void, galaxies shimmering like distant lanterns. Yet within their cores lies a darkness denser, heavier, more enigmatic than even black holes dare reveal. For while black holes swallow truth, neutron stars whisper it. Their light, their pulses, their magnetic storms reach us across centuries of space, carrying fragments of a secret that refuses to die. Scientists lean over chalkboards and computer screens, their equations unraveling beneath the sheer force of these objects. Telescopes the size of cathedrals strain to catch their signals. Faint pulses, fleeting flashes, gravity's ripple carried through space-time itself. Every clue seems to promise an answer, yet each answer collapses into another riddle. What happens to matter when it is pushed beyond breaking? What lies inside a sun so heavy that it became smaller than memory, denser than thought, stranger than truth itself? The neutron star is both an ending and a beginning, the death of a star, and the birth of a mystery that may one day reveal what the universe is truly made of. At the dawn of the 20th century, the heavens still seemed eternal. Stars, fixed in their constellations, appeared to be unchanging guardians of the night sky. For thousands of years, they were thought to be infinite fires, immune to time and death. Yet, as telescopes grew sharper and physics turned inward to the hidden world of the atom, cracks began to appear in that illusion of permanence. The first whisper came from Sirius, the brightest star in the heavens. Beside it, astronomers noticed a faint companion, so dim that it was almost invisible against the glare of its brilliant twin. This companion, later called Sirius B, baffled scientists. Its mass rivaled that of the sun, yet its light was faint and its size impossibly small. It was the first white dwarf, a stellar ember, evidence that stars did not live forever, but could fade into dense remnants. In that moment, the immortality of the stars was broken. If a star could burn out and collapse into a faint shard of its former self, then perhaps the universe was more fragile, more dynamic than ancient wisdom had ever allowed. White dwarfs were smaller, denser, and stranger than anything imagined, yet they were only the beginning of the story. In 1933, amid a world between wars, two scientists, Walter Bod and Fritz Zwicky, dared to take the next leap. They proposed that when a massive star exploded in a supernova, its heart might collapse into something even denser than a white dwarf, a star so crushed that protons and electrons fused into neutrons, creating an object no larger than a city, yet as heavy as the sun itself. They called them neutron stars. It was a radical vision. The idea that the wreckage of a dying sun could shrink into something as compact as an atomic nucleus magnified to the size of a mountain seemed almost absurd. The physics of the day was still trembling from the shockwaves of Einstein's relativity, and the recent discovery of the neutron itself, to suggest such stars might exist, was to stare into the very edge of possibility, where imagination and mathematics strained to keep pace with nature. The cultural backdrop only sharpened the drama. Human civilization was teetering, wars rising, empires collapsing. In the laboratories of Europe and America, physics itself was undergoing a revolution. Relativity bending space and time. Quantum mechanics revealing uncertainty at the heart of reality. And nuclear science uncovering the hidden violence inside the atom. Against this stage of upheaval, the idea of a neutron star fit perfectly, a cosmic mirror of human anxiety, a reminder that even suns could collapse, and permanence was an illusion. The shock lay not only in the theory itself, but in its scale. To claim that something smaller than a single city could outweigh the sun, that matter could be crushed until atoms themselves cease to exist, was to rewrite the boundaries of the conceivable. The neutron star was a vision of death so profound it seemed impossible, yet also an invitation, an opening door into one of nature's deepest mysteries. The early discoveries of stellar remnants did more than challenge astronomy. They unsettled philosophy. To see a star not as a timeless beacon, but as a finite flame, was to confront the fragility of the cosmos itself. Sirius B was no longer a distant curiosity. It was a warning. If even the brightest stars in the sky could fade into dense, cold embers, then perhaps the universe was not an endless stage of immortal fires, but a story written in cycles of birth, brilliance, and inevitable death. Every point of light in the heavens might one day collapse into silence. The heavens were no longer immutable. They were mortal, as white dwarfs emerged from the shadows of discovery. Their existence raised a deeper question. What happens when the collapse goes further? A white dwarf is already dense beyond comprehension, its atoms crushed until electrons themselves resist further compression. But nature is relentless. When the mass of a dying star exceeds a certain threshold, even the electrons cannot hold. They merge with protons, forming neutrons, and suddenly the barrier that protects ordinary matter is broken. The collapse continues, unopposed, until the very idea of substance is rewritten. This speculation was what Bod and Zwicky placed before the scientific world. That the death of a giant star might give birth to something so extreme it bordered on the unimaginable. Their vision was more than mathematics. It was a metaphor made real. A star reduced not to ash, nor to dust, but to something akin to a single atomic nucleus, expanded to colossal dimensions. In human terms, it was like imagining the mass of Mount Everest packed into the size of a sugar cube, or the weight of Earth itself compressed into a sphere barely 10 kilometers across. Such comparisons were clumsy approximations, but they were all that human language could offer when confronted with scales that exceeded intuition. The neutron star was not only an astrophysical prediction, it was a rupture in comprehension. Itself, to the scientific community of the 1930s, the idea was staggering. The neutron itself had only just been discovered by James Chadwick a year earlier, a particle that until then had lived in the realm of speculation. To leap from this fragile discovery to the claim that entire stars could be built from neutrons seemed reckless, even fantastical. Many dismissed the idea as little more than science fiction dressed in equations, and yet Bod and Zwicky persisted, their imaginations refusing to bow to doubt. They saw in the cataclysm of a supernova not just destruction, but transformation, a cosmic alchemy in which a star's death throes might forge the densest object nature could allow before collapsing into the abyss of a black hole. Beyond the mathematics, there was an eerie symbolism. Neutron stars were born in the collapse of giants, explosions so violent they could briefly outshine entire galaxies. In their death, massive stars scattered the elements of life into space, seeding the universe with carbon, oxygen, and iron. Yet at the heart of that violence, something even stranger was left behind, a shard of unimaginable density, a monument to pressures and forces that human technology could never replicate. In a world still trembling from global wars and the rapid dismantling of old certainties, the neutron star became a fitting symbol. It was both terrifying and fascinating proof that the universe was not static but alive, unpredictable, and governed by laws that reached far beyond human understanding. For a time, the neutron star remained no more than a theoretical shadow. No telescope could yet reveal them. No instrument could confirm their existence. They lived on the edges of scientific imagination, supported by equations but unanchored to evidence. And yet the idea lingered, a ghost in the minds of physicists and astronomers, waiting for the moment when the universe itself would reveal whether these cosmic corpses were real. When the idea of the neutron star was first cast into the scientific world, it did not land with the weight of revelation, but with the fragility of speculation. To many of the leading thinkers of the time, the proposal by Bod and Zwicky sounded less like sober astrophysics and more like a tale borrowed from the realm of imagination. Theirs was a universe where stars lived, burned, and died. But the suggestion that one could collapse into something so dense that matter itself was stripped of identity seemed excessive, even absurd. The problem was not in mathematics. On paper, the equations permitted such a fate. General relativity, only a few decades old, allowed for stellar collapse. Nuclear physics, fresh with the discovery of the neutron by James Chadwick in 1932, hinted at new forms of matter that might emerge under extreme pressure. Yet equations are not proof, and speculation is not observation. The scientific method demands more than possibility. It demands evidence, and in the 1930s, no telescopi, no instrument, no human eye could point to the sky and say with certainty, there is a neutron star. The skepticism was natural. The cosmos, after all, has always presented ideas that stretch belief to its breaking point. Even Einstein himself had once resisted the notion of black holes, dismissing them as mathematical curiosities rather than physical realities. To claim that a star could shrink into a sphere the size of a city while retaining the mass of the sun seemed a step too far. Such an object would be nearly invisible, faint to the point of erasure, detectable only through effects that astronomers had no means of measuring at the time. There was also the haunting question of stability. Could such a bizarre state of matter even exist for long? If neutrons could indeed form the body of a star, would they not collapse further under their own gravity, falling past the threshold into a black hole? Some argued that neutron stars were impossible halfway points, temporary ghosts that nature would never allow to linger. Others imagined them as fleeting stages, collapsing in moments, leaving behind only the silence of a singularity. The tension between theory and reality mirrored the wider uncertainty of the age. Physics itself was in upheaval, reshaped almost overnight by the revolutions of relativity and quantum mechanics. Concepts that once seemed stable, space, time, matter, were now fluid, uncertain, trembling under the weight of discovery. To add neutron stars to this growing storm felt like too much, a step into a territory where even the laws of physics began to blur. And yet, there was a kind of beauty in the audacity. Humanity was reaching into realms beyond intuition, probing questions that stretched the imagination to breaking. To envision a neutron star was to confront scales that the mind was never built to hold. A teaspoon of matter outweighing mountains. Magnetic fields powerful enough to reshape atoms. Gravity bending the very fabric of space-time. The human intellect could write these truths into equations, but the human imagination could scarcely keep up. It was like trying to imagine infinity, a concept that could be spoken, written, calculated, but never truly felt. Neutron stars, in those early years, were like infinity made real. an impossible idea waiting for the universe to confirm or deny its existence. Skepticism was not a dismissal, but a pause, a moment of breath before the cosmos revealed its next secret. The discovery of the neutron itself had only just begun to settle into the scientific consciousness when Bod and Zui proposed their startling vision. In 1932, James Chadwick had confirmed the existence of the neutron, a particle without charge, invisible to the senses, known only through the subtle fingerprints it left in experiments. It was a ghost inside the atom, bound tightly to protons in the nucleus, holding matter together with forces that defied ordinary comprehension. To take this elusive particle and imagine an entire star composed of it was almost a leap too far. It was as if the universe had whispered a new word into human language, and before it had even been understood. Theorists were writing poems from it. The scientific community hesitated. The neutron was still a stranger, and its properties were barely charted. Physicists were still struggling to measure its mass, its magnetic moment, its interactions. Nuclear physics was in its infancy, with equations that often broke apart under the pressure of new data. The suggestion that an entire celestial body could be made of neutrons seemed premature, speculative, perhaps reckless. Even in an era already revolutionized by quantum mechanics and relativity, this was an idea that strained the limits of imagination. Part of the resistance stemmed from visibility. White dwarfs had at least been glimpsed, their faint glow revealing themselves to careful observers. But neutron stars, if they existed, would be hidden behind veils of distance and darkness. They would not shine with steady light, for their surfaces were small, their heat rapidly fading, their radiance drowned by surrounding stars. They would be, in essence, invisible. For astronomers accustomed to relying on sight, on glass, mirrors, and photographic plates, the idea of something real but unseen was difficult to accept. Without light, without proof, what could be said with certainty? And then there was the abyss of collapse itself. General relativity had already unveiled black holes as a possibility, though many still refused to believe in them. The mathematics was clear. Beyond a certain density, gravity would overwhelm all forces, crushing matter into a singularity, a point beyond space-time. Neutron stars seemed to live on the edge of this precipice. Could they really exist, balanced on the razor-thin line between stability and annihilation, or would nature simply sweep them past that edge, letting them fall into darkness? To imagine stars held together not by fusion but by the degeneracy of neutrons was to place faith in a fragile equilibrium, one that many doubted could hold. The skepticism carried with it an emotional weight. Humanity was beginning to encounter scales of nature that were almost unbearable to the mind. On Earth, matter was familiar. Stones, oceans, air, even atoms, once strange, had become manageable with the tools of quantum theory. But neutron stars hinted at matter beyond matter, densities beyond comprehension, forces stronger than anything that could be recreated on Earth. To believe in them was to believe that the universe contained regions where the very laws of familiarity broke down, where even imagination faltered. It was like staring into the idea of infinity and realizing it was not abstract but real, embodied in objects drifting unseen among the stars. The early reactions to neutron stars reveal something profound about the human condition. The instinct to doubt when faced with the unimaginable, the tension between what mathematics declares and what observation confirms, the reluctance to accept truths that cannot yet be seen. In the 1930s, neutron stars were both an elegant prediction and a ghost story. They haunted the pages of journals and the chalkboards of physicists, waiting for a signal, a trace, a pulse of light that would prove they were not merely figments of speculation. Until then, they remained in limbo, suspended between theory and myth, equations and disbelief, science and silence. For decades, the idea of neutron stars lived only on paper, a theoretical ghost haunting the margins of astrophysics. They were equations without echoes, whispers of matter compressed to unimaginable density, waiting for the universe itself to betray their presence. And then, in the mid-20th century, a new set of eyes was lifted to the sky, not eyes of glass and silver, but of radio, tuned to the invisible music of the cosmos. Radio astronomy had begun almost by accident, when the static in early telecommunications revealed signals that did not belong to Earth. From that discovery grew an entirely new way of listening to the universe. Antennas replaced telescopes, waves replaced light. And in those unseen frequencies, the sky revealed secrets that had been hidden for eons. It was in this invisible spectrum that the first neutron stars would make themselves known. In 1967, a young graduate student named Jocelyn Bell Burnell monitored miles of tangled wire connected to a radio array near Cambridge. Night after night, paper scrolls of data spilled from the machines, a steady hum of cosmic background broken only by irregular disturbances. And then it appeared, a signal so precise it seemed artificial, a heartbeat from the stars, repeating every 1.3 seconds with unwavering regularity. At first it was catalogued with hesitation, even humor. The team nicknamed it LGM-1 for Little Green Men, but the universe does not speak in jest. The signal was no alien transmission. It was the pulse of a neutron star, a rotating sphere barely the size of a city, spun with such speed and precision that it swept beams of radiation across space like the beam of a cosmic lighthouse. Each time the beam crossed Earth's line of sight, the radio telescopes recorded its call. What theory had long whispered was suddenly undeniable. Neutron stars existed. They were real, their presence carved into the noise of the universe, their pulses like the ticking of celestial clocks. The revelation struck the scientific community with the force of a supernova itself. In a single moment, decades of speculation transformed into fact. The impossible had become observable, yet with proof came new questions. How could such a small object spin so quickly without tearing itself apart? What strange physics allowed matter to endure at such density? What did the core of such a star truly contain? Neutrons compressed like a single colossal nucleus, or something even more exotic, quarks dissolving into a fluid state of pure nuclear essence. The pulsars illuminated more than the night sky. They illuminated the boundary between the known and the unknowable. Humanity had found its first evidence of matter in its strangest form, a fragment of creation that mocked intuition and defied analogy. The stars had revealed themselves, but not their secrets. What lay within them remained hidden, locked behind a crust of unimaginable gravity, guarded by the very laws of physics that had created them. From the hum of radio static, a new era of astronomy had begun. The universe had answered the doubts of skeptics, not with silence, but with rhythm, steady, unyielding, eternal. The neutron stars were no longer ghosts. They were lighthouses, keepers of time, reminders that even in the darkest stretches of space, there are voices that will not be quiet. Under the patient sweep of radio waves, the 1967 discovery of pulsars spread through the world of science like a shockwave. At first, the signal seemed too strange to belong to the natural cosmos. Its precision was unsettling. No earthly machine could maintain such rhythm. No known star could beat so fast and so steady. When Anthony Hewish and Jocelyn Bell Burnell presented the data to colleagues, many leaned forward in disbelief, as though listening for a hoax concealed between the lines of paper. Yet the pulses were real, carved into the fabric of space itself, arriving across vast gulfs of silence with mechanical certainty. One source became two, then three, then dozens. The more scientists looked, the more the universe filled with these cosmic clocks, all ticking in their own precise cadences. The joke of little green men quickly fell away. What remained was something far more profound. Nature itself had constructed engines of time from the remnants of death. The conformation of neutron stars changed more than astronomy. It rewrote the relationship between theory and observation. For 3 decades, Zwicky and Bod's idea had lingered at the edges of credibility. Too wild to dismiss, too intangible to prove. Now, suddenly, the universe had given its answer. Theorists returned to their blackboards, dusting off equations written in the 1930s, finding in them a new life. Observers scoured the sky, reinterpreting strange radio signatures with fresh eyes. The neutron star had moved from speculation to reality, and with it came the birth of a new discipline. No longer was astrophysics confined to light and heat. It now dealt with the invisible, with signals hidden in frequencies beyond human senses, with stars that were not blazing giants, but compressed skeletons. Yet, even as pulsars confirmed the existence of neutron stars, they also deepened the mystery. Their precision and stability hinted at an internal order, but what order could survive under such monstrous conditions? Within their crusts, atoms were stripped bare, protons and electrons crushed into neutrons by gravity's iron hand. But even neutrons, the building blocks of nuclei, might not hold under such pressure. The possibility arose that matter itself could dissolve, neutrons unraveling into seas of quarks, or condensing into forms of matter never encountered in any laboratory. Each pulse of radio waves was a message written in code. We exist, but you cannot yet know us. The human element of this discovery added its own quiet drama. Jocelyn Bell Burnell, a young woman navigating a male-dominated scientific world, became the first to see what no one else had ever witnessed: the heartbeat of a neutron star. Her patience in combing through miles of paper records, her unwillingness to dismiss anomalies as mere noise, became the unlikely bridge between theoretical imagination and empirical reality. Though the Nobel Prize for Pulsars would later bypass her name, the moment of discovery carried her signature, reminding us that science is often advanced not only by the great architects of theory, but also by the quiet persistence of those who listen when the universe whispers as pulsars multiplied in the sky. They revealed themselves not merely as curiosities, but as tools. Their incredible regularity allowed astronomers to map the galaxy with unprecedented precision. Some pulsars spun hundreds of times per second, their beams so constant they rivaled the best atomic clocks on Earth. In them, humanity found a new way to navigate the stars, a celestial GPS etched in the remains of collapsed suns. Yet, beneath this practical triumph lay the haunting core of the discovery. If pulsars were the surface phenomena of neutron stars, what unimaginable storm of physics raged within? The pulses were like the drumbeat of a distant heart, steady but unreadable, reminding scientists that they had only scratched the surface of a deeper, darker truth. And so, the discovery of pulsars stood as both revelation and riddle. The cosmos had answered a question, but only to pose others in its place. Neutron stars were no longer hypothetical, no longer confined to the chalk dust of blackboards. They were real, spinning, pulsing, singing their eerie songs across the void. Yet their interiors remained as inaccessible as the heart of infinity itself. Humanity had caught its first glimpse of matter in its strangest form, but the curtain had only been lifted a fraction, and the stage beyond remained cloaked in shadows. The confirmation of pulsars had opened the door, but what followed was a revelation beyond imagination. when astronomers lifted their gaze beyond radio waves and built instruments to detect the most violent forms of light, X-rays and gamma rays, the universe revealed that neutron stars were not one story, but many. These stellar remnants, each only a dozen kilometers across, came in different guises, each stranger than the last. Some were found in binary systems, locked in desperate gravitational embraces with companion stars. As matter was torn from the partner, it spiraled toward the neutron star, crashing onto its surface in titanic bursts of X-ray light. These became known as X-ray pulsars, their brightness flickering like a heartbeat amplified to cosmic scale. For the first time, humanity witnessed the feeding of these stellar corpses, the way they could siphon life from a nearby star and convert it into bursts of pure energy. But stranger still were the magnetars, neutron stars with magnetic fields so intense they defy comprehension. 1,000,000,000,000 times stronger than Earth's, these fields could twist atoms into unfamiliar shapes, fracture their own crusts, and unleash bursts of radiation powerful enough to be detected across the galaxy. A magnetar's field could, in theory, wipe every credit card on Earth clean of its data from halfway to the moon. A reminder that these objects do not merely exist, they dominate, reshape, and distort reality itself. Their occasional flares, brief but catastrophic, are warnings from nature's arsenal, telling us that the universe still holds weapons beyond our capacity to control or withstand. Yet, neutron stars did not reveal themselves only in isolation. Sometimes they danced together. In rare binary systems, two neutron stars spiral toward each other in a slow, doomed embrace, losing energy as they emitted gravitational waves, ripples in the very fabric of space-time. For decades, Einstein's equations predicted this phenomenon, but it remained an untested dream until September 2015, when LIGO first captured gravitational waves from colliding black holes. 2 years later, on August 17, 2017, the world felt a deeper tremor. GW170817, the merger of two neutron stars. The detection was more than just a signal. It was a chorus of messengers. Telescopes across the globe captured the faint afterglow in visible light. Satellites detected the accompanying burst of gamma rays. Neutrino detectors strained for the ghostly particles that slipped through matter almost without trace. For the first time in history, humanity listened to a single cosmic event through multiple senses, a symphony of observation. Multi-messenger astronomy had been born, and with it came the proof that neutron star collisions were the forges of the universe's heaviest treasures. In the kilonova's afterglow, scientists traced the spectral fingerprints of gold, platinum, and rare elements scattered into the cosmos. The heavy atoms that civilization treasures, the jewelry adorning human bodies, the circuitry powering technologies, the metals passed down through generations, all whispered of a violent origin. Each ring of gold on a hand, each speck of platinum embedded in machines, was born in the death spiral of neutron stars. Every human carries, unknowingly, a fragment of these cataclysms. Matter tempered in collisions so fierce that they shook the geometry of space-time itself. The discovery bound humanity to the cosmos in a new way. Stars were no longer just the distant lamps of night, but ancestral forges, their deaths etched into the elements of human life. The neutron star, once a shadow of theory, had become a storyteller. In its signals and collisions, it revealed the origin of matter, the endurance of gravity, the mutability of space-time. It told of destruction that gives rise to creation, of death that scatters seeds for new worlds, of silence broken by the pulse of eternal clocks. And in that realization lay a profound humility, the recognition that the universe is not just observed from afar, but carried within. To touch gold, to where it is, to touch the ashes of stars that once collided in violence. To exist at all is to embody the echoes of neutron stars. Their mystery is not only in the heavens, it is here, woven into the hands that reach for them. The merger of neutron stars in 2017 did more than confirm predictions. It shifted astronomy from a science of passive watching into one of participation, as though the cosmos had opened a dialogue. For decades, scientists had chased isolated signals, light in one spectrum, radio waves in another, gravitational theories untested in the silence of mathematics. But with GW170817, nature spoke in chords. The trembling of space-time was accompanied by flashes of gamma rays, by lingering X-ray afterglows, by the slow fading of visible light that telescopes tracked across weeks. Hundreds of observatories turned their gaze toward a single patch of sky, each capturing a different voice of the same event. For the first time, humanity became witness to a cosmic symphony, not a solitary note. This union of messengers revealed a truth more powerful than any one detection, that the universe could be understood more fully when all its languages were heard together. The kilonova that followed the merger became a laboratory unlike any other. As the fading light passed through spectrographs, it carried the signatures of freshly forged elements. Gold, platinum, and uranium shimmered in its spectrum, written in lines of light as clear as a declaration. These were not the products of ordinary stars, nor of the familiar furnaces of fusion that power suns. They were children of catastrophe, born in seconds of violence as two collapsed suns tore each other apart. The jewelry in a box, the circuitry in a computer, the rare metals buried in the Earth's crust, all of them carried the memory of explosions so distant and ancient that their light only now reached human instruments. To hold such metal was to hold the aftermath of colliding neutron stars, to cradle the wreckage of ancient deaths. The philosophical weight of this truth was profound. For centuries, gold had been a symbol of permanence, of earthly wealth and eternal value. Kings wore it as crowns, civilizations marked it as treasure. Yet its true origin was revealed to be impermanence itself, the fleeting, catastrophic violence of colliding stars. Permanence was forged from destruction. Eternity was written by death. To wear gold was to unknowingly wear the history of the cosmos, to bind one's life to the cycles of stellar creation and decay. Every wedding ring, every coin buried in the soil of forgotten empires, every ornament carried through history, each bore silent testimony to Neutron, stars that died so others might live. But beyond poetry, there was physics, and physics demanded to know more. Gravitational waves carried details about the mass and radius of the colliding stars, whispering about their inner makeup. Were they composed purely of neutrons, crushed to unimaginable density? Or did they hide stranger interiors, quark matter, hyperons, exotic states that no laboratory could recreate? The precise shape of the gravitational wave signal contained clues, like the fingerprint of matter at its breaking point. The world's detectors strained to extract every nuance, every curve of the wave, knowing that inside those patterns lay the first hints of what matter becomes when it is stripped of all structure. When it is pushed past the limits of atomic identity, the human response to the event was as extraordinary as the science. Coordinated networks of astronomers, working across continents and disciplines, joined in a moment of unity. Physicists who had devoted their lives to the mathematics of gravity found themselves suddenly connected to optical astronomers, to neutrino hunters, to particle theorists. In the silence of deep space, a merger had called forth a collaboration on Earth unlike anything before it. The cosmos had stitched together not only messengers of physics, but the efforts of humanity itself. It was as if the neutron stars, in their final act, had extended a hand across space-time. reminding a fragmented species of its shared curiosity, its shared origin, its shared awe. And still, the mystery deepened. If collisions could give rise to the heaviest elements, how many such events had seeded the universe? Were the Earth's own veins of gold and platinum the result of a single cataclysm billions of years ago, or the layered remnants of countless mergers scattered through cosmic history? Each possibility carried its own poetry. Perhaps the planet humanity called home was enriched by a single titanic collision, its debris sweeping through the galaxy until it coalesced into worlds. Or perhaps every element was the sum of thousands of stellar deaths, a mosaic of violence and rebirth written into the very atoms of existence. To gaze upon a neutron star merger was to confront the paradox of the universe itself. Out of collapse came creation. Out of destruction, new order. In the death throes of stars, nature wrote the materials of life, technology, art, and meaning. The discoveries of X-ray and gamma-ray astronomy, the revelations of gravitational waves, the dawn of multi-messenger science, all pointed toward one truth. The mystery of neutron stars was not confined to the heavens. It pulsed in the rings on fingers, in the circuits of machines, in the silent weight of metals carried through generations. Humanity itself was an extension of these cosmic deaths, bound by invisible threads to the most violent and most beautiful events in the universe, the triumphs of radio waves, X-rays, gamma rays, and even the trembling chords of gravitational waves had proven beyond all doubt that neutron stars exist. They had revealed themselves in pulses, in flares, in collisions so violent they shook the very geometry of space. Yet beneath all of this revelation, one question remained sealed away, untouched and impenetrable. What lies within? No telescope, no detector, no instrument built by human hands can pierce the crust of a neutron star. Their interiors remain hidden behind walls of gravity so immense that even photons cannot emerge, carrying direct information about what they conceal. Observers are left instead with shadows and echoes, with signals that hint at what might be happening, but never show it outright. This is the great paradox of neutron stars. They are at once the most studied remnants in the cosmos and the most elusive. Humanity knows they exist, can trace their orbits, can measure their masses with exquisite precision. Yet what composes their hearts remains one of the greatest unsolved riddles in physics. At the center of the mystery lies the equation of state, the mathematical description of how matter behaves under pressures and densities utterly beyond human comprehension. On Earth, matter bends and yields according to familiar rules. Steel resists compression, gases expand, liquids flow. But inside a neutron star, a single teaspoon of material would weigh billions of tons, crushing every known law of material behavior into irrelevance. How do neutrons, subatomic particles, normally content to cluster gently inside atomic nuclei, behave when crammed together by gravity's relentless grip, pressed into a space no larger than a human city? Physicists propose competing models, each as exotic as the last. In some, the star's interior is a rigid lattice, with neutrons packed together like bricks in a cosmic wall. In others, the pressure grows so extreme that neutrons dissolve, their constituent quarks liberated into a sea of pure nuclear essence, a quark gluon plasma, frozen not by heat but by density, something never glimpsed outside the most powerful particle colliders. Still more speculative models suggest even stranger phases, hyperons, particles containing strange quarks, or condensates of mesons, behaving like quantum superfluids on a stellar scale. Each theory paints a different picture, yet all share the same haunting uncertainty. The tension between theory and observation deepens this puzzle. Astronomers measure neutron stars through the timing of pulsars. through X-ray surface emissions, through the distortions in gravitational wave signals from collisions. These measurements yield mass and radius estimates, but they do not align cleanly with any single model. Some neutron stars appear too massive to be explained by conventional neutron packing, implying that some new state of matter must resist collapse. Others appear smaller than expected, hinting at cores so soft that matter behaves in ways physics has yet to describe. The data points form a constellation of contradictions, each observation illuminating the edges of the mystery but never its center. In this space of uncertainty lies a profound possibility that neutron stars may represent a missing link, a bridge between the known universe of particles and the elusive frontier of quantum gravity. At their cores, densities approach those of black holes, yet the stars do not collapse. They balance on the razor's edge between existence and oblivion. If gravity can be balanced here by quantum forces, then neutron stars may be the natural laboratories where Einstein's relativity and the quantum world are forced to meet. They may hold the key to unifying the two greatest theories of modern science, not in equations on chalkboards, but in the silent interiors of collapsed suns. Thus, even as human ingenuity expands, even as new instruments listen across the spectrum of cosmic signals, the neutron star keeps its greatest secret guarded. It allows glimpses of its surface. It speaks in pulses and tremors, but its heart remains hidden. The closer science comes, the more the mystery deepens, as though the universe is reminding us that there are truths which must be pursued but never easily given. The neutron star becomes, in this sense, a mirror. In its silence, humanity sees the limits of its own knowledge. In its paradoxes, it glimpses the unfinished story of physics. And in its mystery, it confronts the humbling truth that the cosmos is not obliged to yield its secrets, no matter how desperately they are sought. To study the unknowable, scientists have built instruments of remarkable delicacy. One such sentinel orbits aboard the International Space Station, NASA's NICA telescope, the Neutron Star Interior Composition Explorer. It peers into the cosmos not with glass lenses, but with X-ray detectors designed to capture the faint flicker of radiation streaming from pulsars. By watching the tiny hotspots that whirl across a neutron star's surface as it spins, NICA can infer both the star's size and its mass, drawing a faint outline around the mystery within. With each measurement, physicists test the competing equations of state, comparing the predictions of dense matter models with the reality of the star's pulse. And yet, like shadows in a cave, the outlines are never sharp. Some observations favor stars larger and stiffer, others point toward smaller, softer interiors. The truth remains suspended in between, elusive as starlight through mist. The struggle is not only observational, but philosophical. For centuries, physics has thrived by reducing nature into parts, by breaking down the world into ever smaller building blocks. Atoms gave way to nuclei, nuclei to protons and neutrons, protons to quarks and gluons. But inside neutron stars, reduction falters. The pressures are so immense that matter no longer behaves as discrete particles. It becomes a continuum of nuclear essence. The categories of physics blur, and language itself becomes inadequate. A neutron star is not a ball of neutrons in any simple sense. It is an ocean of matter that may be both solid and liquid, both particle and field. A liminal state where familiar distinctions collapse. To describe it is to acknowledge the limits of human imagination. There is a haunting symmetry in this. Black holes, to conceal their interiors, veiling them behind horizons from which no information escapes. But neutron stars are different. They reveal themselves just enough to torment us, offering fragments of data, numbers that tantalize but never converge. They sit on the knife edge between the visible and the hidden, between the measurable and the unknowable. To confront a neutron star is to confront the boundary where human science brushes against cosmic indifference. And yet, perhaps, it is this very tension that makes them so profound. If their interiors were simple, if equations closed neatly, the mystery would fade into comprehension. Instead, the discordant data keeps the field alive with questions. Are the cores of neutron stars seas of quark matter, droplets of the universe's earliest moments preserved within stellar coffins? Or do they harbor phases of matter never yet imagined, new states that demand not only new theories, but new philosophies of nature itself? Each possibility hints at a deeper truth, that neutron stars are not just remnants of collapsed suns, but windows into the unfinished story of physics, living relics of a universe still unfolding. For now, the answer remains sealed. No spacecraft can land upon a neutron star's surface. No probe can burrow into its depths. Humanity is confined to watching from afar, building ever more sensitive ears to the cosmos, and waiting for the next signal. Perhaps it will come in the rumble of gravitational waves from another stellar collision. Perhaps in the silent track of a neutrino, whispering from the heart of a dying star. Until then, the mystery deepens, stretching like an abyss across the frontiers of knowledge. The neutron star, in its silence, becomes a kind of cosmic oracle. It will not speak directly, but it invites questions that reshape science itself. It reminds us that the universe is not a solved puzzle, but a living enigma, vast enough to contain surprises beyond imagination. And in the quiet spaces between pulses, humanity is forced to reckon with both its brilliance and its smallness, caught between the desire to know and the humbling realization that some truths remain locked inside the stars. At the boundary where theory meets impossibility lies the realm of the neutron star. To understand its interior is to chase a dream that earthly laboratories can barely begin to touch. The densities inside such a star rise to billions of tons packed into the space of a teaspoon. No machine on this planet, not even the most advanced particle accelerator, can squeeze matter to such crushing extremes. The Large Hadron Collider at CERN, humanity's most powerful probe of the subatomic world, collides nuclei at near-light speed, creating fireballs of quark-gluon plasma that mirror conditions a microsecond after the Big Bang. Yet, even these brief flashes of primordial matter are pale imitations compared to the relentless, eternal pressures inside a neutron star's heart. On Earth, matter reverts back to normal in less than a blink. In the cosmos, neutron stars sustain those impossible states for millions, even billions of years. Physicists turn to mathematics where experiments cannot reach. Supercomputers are tasked with simulating neutron star matter, solving equations that combine nuclear forces, quantum mechanics, and the curvature of space-time. But here, too, nature resists. As the models are pushed deeper, beyond the crust and into the core, the equations spiral into instability, collapsing into numerical chaos. Each attempt reveals only fragments of truth, not the whole. Like explorers lost in fog, scientists move forward with maps that dissolve the closer they approach the center. Einstein's general relativity, the great theory of gravity, provides part of the framework, describing how mass warps space-time to hold such a star together. Quantum mechanics, the theory of the very small, explains how neutrons resist collapse through degeneracy pressure, a kind of subatomic scaffolding that prevents them from occupying the same quantum state. Yet even these towering pillars of physics bend under the weight of neutron star reality. Gravity pulls inward with unstoppable force, while the laws of quantum pressure push outward in defiance. It is a cosmic tug-of-war where the rules of two separate realms clash, and no referee exists to reconcile them fully. This makes neutron stars not just astrophysical objects, but crucibles at the extreme edge of science. They serve as natural laboratories where human theories are tested to their breaking point. Each observation, each flicker of X-ray or ripple of gravitational waves, is not merely data. It is a challenge, a question carved into the night sky, asking whether the union of quantum mechanics and relativity is still incomplete. If black holes mark the places where space and time collapse, neutron stars mark the precipice before that fall, a precarious balance where matter itself hesitates between existence and oblivion. To look at a neutron star, even through numbers and equations, is to feel the fragility of human knowledge. These objects remind us that physics, for all its precision and elegance, is still a work in progress. They demand a language beyond what science yet possesses, a union of ideas not yet forged. Until that day comes, neutron stars will continue to stand at the frontier, silent guardians of secrets that could redefine the laws of reality itself. And so, the struggle continues. In laboratories across the world, physicists attempt to mimic, even for a fraction of a second, the infernal pressures locked inside these stars. Heavy ion colliders smash gold or lead nuclei together at velocities approaching light, compressing matter until it briefly resembles the dense soup believed to fill neutron star cores. Detectors strain to capture the fleeting signatures, jets of particles, showers of quarks, whispers of a plasma hotter than any furnace in the universe. But the attempt is always imperfect. Gravity, the invisible sculptor that binds neutron stars, cannot be reproduced in a particle ring. Earth has no way of summoning a gravitational pull billions of times stronger than its own. Every experiment becomes a shadow play, an echo of the real thing, a glimpse that fades the moment it appears. Computers, too, are asked to bridge the abyss. Vast arrays of processors simulate the nuclear equation of state, the ultimate description of how matter behaves when it is stripped, crushed, and remade. Yet the models are haunted by instability. Push the simulation too far, and the code collapses into errors, producing impossible results, negative pressures, runaway infinities, equations that no longer describe a universe we know. It is as if the mathematics itself recoils, unable to bear the truth of what lies at the heart of these stars. In this way, the neutron star is not only a frontier of physics, but a frontier of computation, a problem so vast that even machines stumble under its weight. At the center of this challenge lies the tension between two great pillars of human thought. Relativity describes the grand curvature of space and time, the way matter tells the cosmos how to bend. Quantum mechanics describes the microscopic struggle, the restless particles forever obeying uncertain rules. Yet inside neutron stars, these domains collide. The equations of Einstein and the principles of quantum physics must coexist in one place, and the union is uneasy. One predicts collapse, the other resists it. One curves the universe itself, the other defends the fabric of matter from destruction. And in the middle of this clash stands the neutron star, balancing between two worlds of thought that remain, to this day, unresolved. What emerges from this tension is a haunting possibility that the universe is stranger than either theory allows. Perhaps, deep within the neutron star, matter ceases to be neutrons at all. Perhaps the particles melt into quark matter, a primordial fluid more ancient than the oldest star, a reminder of the cosmos as it was in its first breath. Or perhaps something even more exotic takes form. Hyperons, condensates, states of matter no experiment has ever glimpsed. Each hypothesis represents a different path, but the evidence is not yet enough to choose. Observations of neutron stars, masses, and radii offer conflicting hints. Some suggest stars heavier than 2 suns can remain stable, forcing theorists to strengthen their models. Others suggest certain stars are smaller and denser than any model can accommodate. Between these contradictions lies the unanswered question: what truly exists at the heart of these stellar corpses? To confront this question is to confront the limits of human knowledge itself. Every telescope, every detector, every accelerator is a hand stretched toward the unreachable. And yet, the pursuit continues, because the stakes are not merely astrophysical. Neutron stars may hold the key to unifying the great theories of physics, to answering how the universe binds its smallest parts with its largest structures. They are the unfinished sentence in the language of reality, waiting for a word that has not yet been invented. At the heart of mainstream physics lies the simplest, and perhaps most intuitive, picture of a neutron star, an immense sphere of neutrons, squeezed together by gravity until they are packed like bricks in a wall. In this model, the neutrons dominate, but not alone. Between them slip a fraction of protons and electrons, threads of charge woven into the otherwise neutral mass. To describe it is to describe matter in a form unrecognizable to daily experience, yet still governed by rules that echo those of the atomic world. Here, nuclei have lost their individuality, electrons have been crushed into protons, and the building blocks of ordinary matter dissolve into a dense, featureless sea. It is a universe reduced to its simplest grammar: neutrons, protons, and electrons, bound by gravity into an eternal stillness. And yet, even within this neutron soup, matter does not rest in uniform silence. At certain depths, theorists predict bizarre structures known as nuclear pasta, where atomic nuclei organize themselves into strange, elastic patterns. Instead of remaining spherical, they stretch into spaghetti-like filaments, flatten into lasagna-like sheets, or curl into gnocchi-like clumps. These shapes are not whimsical imagination. They are solutions to the equations of nuclear physics at densities just below the star's inner core. In such arrangements, matter becomes as much a crystal as a liquid, a labyrinthine network of geometry and force. If true, this nuclear pasta would be among the strongest materials in the universe, able to withstand pressures that no terrestrial substance could endure, bending but never breaking under stresses that would shatter steel like glass. Beyond this outer structure lies something even more alien, a heart where friction ceases to exist. The dense neutron fluid, it is believed, slips into a state of superfluidity, a phase of matter in which particles flow without resistance, without heat, without end. To imagine this is to imagine an ocean that never slows, never stills, a river flowing forever without losing strength. Alongside this superfluid exists superconductivity, where protons form pairs and allow magnetic fields to tunnel through the star in quantized vortices, spinning threads of energy that pierce its core. These invisible patterns may be the architects of the star's stability, dictating its spin, its radiation, and its subtle tremors. The evidence for such exotic states does not come from theory alone. The cosmos itself has offered hints, encoded in the behavior of pulsars. These neutron stars, rotating with unerring precision, sometimes betray themselves with sudden glitches, abrupt jumps in their spin rate, as though something deep inside has shifted. For decades, astrophysicists have traced these glitches to the hidden superfluid interior. When the superfluid rotates at a slightly different pace than the solid crust, tension builds. Then, in a moment, it slips, transferring angular momentum to the crust above, and the star spins a little faster. Each glitch is a message from the unseen heart, a seismic whisper from a realm no probe will ever touch. On the International Space Station, the NASA telescope continues to refine these mysteries. measuring the sizes and masses of neutron stars with unprecedented precision. By capturing the subtle X-ray pulses emitted as hotspots rotate in and out of view, NASA allows astronomers to weigh and measure stars no larger than a city, yet heavier than entire suns. These measurements, when paired with theoretical models, slowly carve away at the uncertainty surrounding the equation of state. Some models are ruled out, others survive, but none yet claim the final answer. Each new data point is a step closer, but the summit remains unseen. Mainstream theories converge on the idea that neutron stars are laboratories of extreme nuclear physics, where ordinary matter is stripped of its familiar form and forced into states that stretch human imagination. The picture grows sharper, but never completes. For every clue offered, pulsar, glitches, X-ray, radii, mass limits, another layer of mystery remains. And so the quest continues, as scientists refine the models, always hoping that the next signal, the next detection, will bring the boundaries of the unknown a little closer to the light. Yet even as the mainstream picture appears to offer a sense of structure, it never quite dispels the strangeness. The notion of neutrons packed together like bricks, forming an immense sphere of nuclear matter, is itself already far removed from the familiar. But when theorists speak of superfluids and nuclear pasta, the line between physics and surrealism begins to blur. The names may carry a hint of playfulness, yet beneath them lies something profoundly alien. A neutron star is not simply a collapsed husk. It is a world where the laws of nature bend into strange geometries, where matter arranges itself into patterns unknown on Earth. In this sense, even the most conventional descriptions remain as eerie and unsettling as the most speculative ones. To consider a neutron star's interior as a superfluid is to imagine an ocean deeper than any ever conceived, flowing with perfect silence. Unlike water, it does not resist motion, does not dissipate heat, does not slow with time. In this infinite stillness, the fluid forms vortices that are themselves quantized, tiny whirlpools governed by the rules of quantum mechanics, their circulation allowed only in discrete steps. These vortices are not small disturbances. They are the invisible scaffolding of the star's rotation, regulating how it spins, how it evolves, and how it releases its bursts of energy. Each vortex is like a needle of geometry carved into the fabric of nuclear matter itself. Together, they remind us that even at scales far beyond the reach of microscopes, quantum laws hold dominion, weaving their strange influence across the cosmos. The idea of superconductivity is equally haunting. Protons, even in such extreme densities, are not free to wander alone. Instead, they pair into delicate quantum bonds, much like electrons in a superconducting wire. In doing so, they create a medium in which magnetic fields cannot diffuse at will, but instead pierce through the star in rigid, quantized filaments. These magnetic flux tubes may twist and tangle over centuries, building up stresses that can suddenly snap, releasing bursts of X-rays or gamma rays that sweep across space. Magnetars neutron stars with fields trillions of times stronger than Earth's may owe their violent tempests to this hidden structure. Thus, within what seems to be a corpse of a star, there exists an interior still alive with motion, with hidden forces and shifting patterns of quantum tension. The pulsar glitches, tiny stumbles in the precision of cosmic clocks, are the universe's most direct messages that this picture is real. They are not merely random errors. They are the signatures of a star's interior struggling to reconcile its parts. The rigid crust above and the frictionless ocean below cannot spin together in perfect unison. Tensions accumulate for decades, even centuries, until they finally break. In that instant, the crust receives the momentum it has long resisted, and the star lurches forward, spinning slightly faster. The world notices it as a fraction of a second adjustment, but behind it lies the release of forces beyond comprehension. For scientists, these glitches are not annoyances but revelations, windows into the hidden superfluid that otherwise cannot be touched. Each event is a reminder that these stars, though silent and distant, are not static tombs but dynamic worlds, restless beneath their calm exterior. Meanwhile, instruments like NICA add weight to the story by offering precision where before there was only guesswork. By measuring the radius of neutron stars with kilometer accuracy, astronomers place strict limits on which models of matter can survive. If a star is too small for its mass, then only the stiffest forms of nuclear matter can explain it. If it is larger, then softer equations of state must be true. Every measurement becomes a knife, cutting away entire classes of theories, narrowing the possibilities. Yet despite this progress, no final answer has emerged. The uncertainties remain, and the equation of state, the ultimate expression of matter under these conditions, refuses to be pinned down. This, perhaps, is the most humbling truth about the mainstream theories. They are at once astonishingly detailed and fundamentally incomplete. They sketch a vivid portrait of interiors filled with quantum fluids, magnetic lattice, and nuclear pasta, yet the details remain blurred, the borders undefined. For all the progress, the heart of the neutron star still holds something back, like a veil drawn just beyond reach. It is not that the theories are wrong, they are too consistent with evidence to be dismissed. But they are not the whole truth either. What lies deeper, at the very center of these stellar corpses, remains a question suspended between what is known and what is still beyond. Imagination, beyond the solid ground of mainstream theories, there stretches a landscape even stranger, a terrain of speculation where the imagination of physics wanders to its limits. If the neutron star's interior is not merely a dense ocean of neutrons, then perhaps it is something far more radical, a place where the very notion of the atom has dissolved, and quarks, the fundamental bricks of protons and neutrons, roam free. This possibility gives rise to the idea of strange quark matter, a phase of matter so exotic that it may be more stable than anything the universe has ever known. If such a state exists, then neutron stars may not be neutron stars at all, but strange stars, composed not of neutrons but of liberated quarks, bound into a fluid sea of up, down, and strange varieties. To picture such a star is to picture a world without nuclei, without atoms, without any of the familiar scaffolding of chemistry, only quarks, stripped of their confinement, drifting in endless symmetry. The idea is both haunting and exhilarating, for it suggests that the universe may prefer this state, that quark matter is not simply an anomaly but a truer ground of existence. If a neutron star were to collapse into quark matter, the transition could unleash signals unlike any seen before, bursts of radiation, shudders of gravitational waves, sudden shifts in spin. Some theorists even suggest that once strange quark matter is born, it may spread like a contagion, transforming ordinary nuclear matter into its own form, rewriting the identity of entire stars. It is speculation, yes, but speculation grounded in the mathematics of quantum chromodynamics, the theory that governs quarks and Yet quark matter is not the only contender in this gallery of exotic interiors. Another possibility lies in the existence of hyperons, particles like neutrons, but stranger, containing heavier quarks in their structure. At sufficient densities, hyperons could emerge naturally, softening the equation of state and changing the balance of forces within the star. Or perhaps the neutrons themselves could condense into kaon fields, collective states of matter that exist nowhere else in nature. Each of these candidates reshapes the star's interior into something unfamiliar, a laboratory for particles that may never be glimpsed on Earth. And there are even wilder ideas still. Some physicists entertain the possibility that neutron stars may harbor dark matter cores, concentrations of the invisible substance that makes up most of the universe's mass. If true, then within these stars might lie the answer to one of cosmology's deepest questions. What is the nature of dark matter? Observations of slight deviations in the spins, masses, or temperatures of neutron stars could, in theory, reveal its hidden influence. In this view, the star becomes a crucible not only for nuclear physics, but for the mysteries of the entire cosmos. What ties these speculative visions together is a sense of thresholds, of transitions that push beyond the borders of the known. Neutron stars, in this light, are not merely the corpses of suns, but gateways, natural laboratories where the familiar rules of the standard model may fracture, giving way to new principles of reality. To peer into their hearts is to look for signs of the unfinished story of physics, for whispers of laws not yet written, and so the image lingers. Inside the darkness of a neutron star may lie not death, but the universe's deepest truth. Perhaps the true building blocks of existence are hidden there, in silence, in infinite pressure, waiting to be discovered. Not in the grand expanse of galaxies or the fiery births of stars, but in the quiet corpses left behind, stars that have collapsed not into nothing, but into something more fundamental than all that came before. If the heart of a neutron star holds quark matter, hyperons, or some other unfamiliar substance, then it becomes not merely an object of astronomy, but a mirror of the universe's unfinished laws. Every hypothesis, from strange stars to dark cores, carries with it an echo of something profound, that the cosmos may not yet have revealed its deepest alphabet. The atoms of Earth, the molecules of biology, even the chemistry of life, may not be the final words of matter, but only the surface crust of something richer and more fundamental. Inside these stellar remnants, beneath crushing densities, that deeper language may be spoken in silence. For scientists, this is both an opportunity and a torment. Observations can only brush the outer skin of these stars. Telescopes like NICA, measuring the light from hotspots circling their magnetic poles, reveal radii and masses with unprecedented precision. Gravitational wave observatories capture the vibrations of entire stars colliding, ripples in space-time that encode clues about their stiffness, their inner compressibility. Yet each dataset is a partial whisper, never the whole sentence. The mysteries at the core remain shrouded, forcing physicists to build bridges of theory across the darkness. The equation of state, the relationship between pressure and density at nuclear extremes, remains the key. But it is a key that may open many doors. Each path leads to a different kind of star, a different destiny for matter itself. Speculation about quark matter is more than idle imagination. In laboratories like CERN and Brookhaven, particle accelerators create droplets of quark-gluon plasma, fleeting fireballs where protons and neutrons melt into their constituents. These states exist only for a heartbeat, before cooling back into ordinary matter. But in the unyielding compression of a neutron star, they might persist indefinitely. What is ephemeral on Earth could be eternal in the cosmos. To think of such a star is to think of a relic that has peeled back the mask of matter, exposing what might lie beneath every proton, every nucleus, every atom that has ever existed. Other models wander into more shadowed domains. If hyperons populate the inner layers of neutron stars, their masses and spins should behave differently than pure neutron models predict. If kaon condensates form, then the star's structure could soften, lowering the maximum mass it can sustain before collapse. Some researchers even suggest that signatures of these exotic states might already be hiding in pulsar catalogs, waiting for the right interpretation. The universe may already be whispering its secrets, though humanity has not yet learned how to listen. But perhaps the most haunting speculation is that of dark matter cores. Dark matter, invisible yet dominant, remains one of the universe's most stubborn riddles. If it can interact with ordinary matter, then neutron stars are its perfect cage, capable of capturing and concentrating it into dense kernels. Such cores would subtly alter the star's mass, cooling rate, and even the signals of its mergers. If confirmed, this would make neutron stars not only remnants of ordinary stellar life, but also repositories of the universe's hidden mass. In their darkness would be preserved not just the ashes of stars, but the very stuff that binds galaxies together. In the end, all these possibilities paint neutron stars as thresholds. They are not simply objects left behind by collapse, but gateways to new physics. In their hearts may dwell the blueprints of creation, matter as it was in the first moments after the Big Bang, or matter as it could be in universes not yet imagined. The search to understand them is not merely a search for astrophysical detail, but for the architecture of reality itself. And so, astronomers keep listening, watching, calculating, reaching into the silence. For beyond the cold light of these stellar corpses may lie the most profound truth of all, that in death, the stars have become keepers of the universe's deepest secrets. Beneath the endless sweep of the sky, the quiet labor of science presses against the walls of the unknown. The riddle of neutron stars, once the domain of speculation, is now pursued with instruments of extraordinary precision, each built to catch the faintest whisper of these celestial remnants. At the International Space Station, the NICER telescope bends its gaze toward pulsars, measuring the subtle flicker of X-ray light that spills from their poles. From these faint pulses, scientists reconstruct the silhouettes of neutron stars, tracing how their immense gravity bends the paths of photons. Each light curve becomes a kind of fingerprint, encoding the star's radius, its surface irregularities, and the unseen pressures buried deep within. It is astronomy reduced to shadows on a wall, yet in those shadows, the outlines of truth emerge. Elsewhere, entire observatories listen not to light, but to space-time itself. Gravitational wave detectors, once silent, now hum with the tremors of colliding neutron stars. The great crash of stellar corpses sends ripples racing across the universe, carrying information about matter at densities unachievable on Earth. As Virgo and Cagra refine their sensitivity, and as next-generation observatories prepare to awaken, the catalogue of these cataclysmic signals will swell. Each merger is not only an event but a probe, a natural experiment in conditions beyond imagination, where matter is squeezed and twisted until even Einstein's equations quiver. On Earth's surface, forests of radio dishes rise like monuments of steel, tuned to the heartbeat of pulsars. China's fast telescope, its vast dish cradled in a mountain valley, listens to millisecond pulses with unmatched clarity. Soon, the square-kilometer array will add its voice, stretching across continents, its sheer scale allowing timing measurements of pulsars with exquisite precision. These cosmic clocks, spinning faster than the blades of a turbine, reveal when their rhythm falters, tiny glitches hinting at superfluid interiors, starquakes, and hidden currents beneath their crusts. Each disruption is a clue, a seismic whisper from a world where seismicity has no earthly parallel. Meanwhile, supercomputers simulate what no laboratory can contain. Equations of nuclear physics are embedded into digital stars, collapsing under their own weight, spinning, colliding, and fragmenting in virtual universes crafted from mathematics. Yet even here the boundaries are sharp. When densities climb toward the unimaginable, the codes falter, their stability lost. The machines remind humanity that the mystery is not only astrophysical, but also computational, pushing against the limits of knowledge itself. Still, each new model narrows the possibilities, carving away the unlikely to reveal what may remain. None of this unfolds in isolation. Across continents and oceans, laboratories collide heavy ions to mimic fragments of neutron star matter. Observatories in orbit coordinate with telescopes on mountaintops. Theorists share their equations with data scientists, who compare their models to pulsar catalogs and merger signals. This is a global effort, an invisible web of collaboration stretching across languages and borders, united by a single question: what lies within? And though the puzzle remains incomplete, there is a sense, quiet but growing, that the mystery is beginning to fracture. Measurements from NASA press against the predictions of nuclear theory. Gravitational waves reveal stiffness and softness that exclude entire classes of models. Pulsar timings suggest interiors richer than once believed. Piece by piece, the great silence of neutron stars is yielding, giving way to patterns. Perhaps not yet answers, but outlines, sketches of a truth once hidden beyond reach. In the faint tremor of space-time, in the rhythm of a distant pulsar, in the bent path of a single photon, the veil is thinning. Humanity stands closer now than ever before, at the edge of a breakthrough, listening for the moment when the stars themselves will finally speak. The road forward is already being built in silence. Plans for the next generation of instruments are drawn not only in engineering blueprints, but in the shared anticipation of a breakthrough. The proposed Einstein telescope in Europe and the Cosmic Explorer in the United States promise to push gravitational wave astronomy into a new era. With their unparalleled sensitivity, they will listen to the universe with an acuity fine enough to catch the merging of neutron stars across vast swaths of cosmic history. Even in the first billion years after the Big Bang, these signals will not only count collisions, but trace how matter itself evolved when the universe was young, hinting at whether the physics of the densest stars has shifted over time. If neutron stars are indeed laboratories of exotic matter, these future detectors will transform their collisions into experiments, written across the fabric of space-time itself, beyond Earth's orbit. Visions of new X-ray observatories wait for their turn to ascend. NASA's proposed StrobeX mission and the European Athena Observatory are designed to peer more deeply into the compact remnants of dead stars. By capturing X-ray spectra in exquisite detail, they would reveal how neutron stars distort the light that escapes them, imprinting signatures of their size, mass, and the strange material that clings to their surface. These observatories would act as microscopes aimed at the cosmos, searching for the fingerprints of superfluids, superconducting interiors, and the nuclear pasta structures that may ripple beneath the crust. They would not solve the puzzle outright, but they would corner it, forcing theories to match reality with unprecedented precision at the same time. Humanity's most ambitious radio astronomy project is taking shape across deserts and grasslands. The square-kilometer array, spread across Australia and South Africa, will become the most powerful radio observatory ever built. With its vast collecting area, it will time pulsars to accuracies once thought impossible, detecting even the faintest hesitations in their rotations. Those hesitations, pulsi glitches, and timing irregularities are not random. They are the scars of hidden processes deep within neutron stars, where superfluid vortices pin and break, releasing sudden bursts of energy. To measure them with such detail is to listen to the whispers of quantum matter under crushing gravity. It is to hear the star quake, to feel its invisible pulse. But even with telescopes and detectors reaching farther and deeper, the puzzle is not confined to the heavens. In nuclear laboratories on Earth, The collisions of heavy ions mimic fragments of the neutron star environment. The relativistic heavy ion collider in the United States and the Large Hadron Collider at CERN recreate the conditions where protons and neutrons begin to dissolve into quark matter. For a fleeting instant, in the chaos of a high-energy collision, temperatures rise and densities surge to values that hint at the same physics sculpting neutron star cores. Scientists sift through the debris of these miniature explosions, searching for the echoes of quark-gluon plasma, for the signs that matter can indeed free itself from confinement. Each result feeds back into the astrophysical models, linking the smallest scales of nuclear forces to the largest scales of collapsing stars. What emerges is a picture of unity. Supercomputers knit together the scattered data, combining NICE's light curves, gravitational wave signals, pulsar timings, and nuclear experiment results into coherent simulations. These digital stars, though imperfect, begin to behave more like the real ones, narrowing the possibilities of what lies within. They collapse, spin, and sometimes shatter, producing synthetic gravitational waves that can be compared against actual detections. When a match occurs, it is more than a computational victory. It is a brief glimpse into the otherwise unreachable. The cosmos itself becomes a dataset, the most ancient laboratory in existence. Still, the work carries with it a weight of humility. Even as progress accelerates, the challenge remains extraordinary. Neutron stars are small, distant, and mercilessly private. Their interiors cannot be probed directly. Their secrets are revealed only through secondary signals, faint distortions of light and space that must be decoded with care. A false step can lead to misleading conclusions, and the history of astrophysics is filled with ideas once thought certain, later overturned. Yet the pursuit continues, because the stakes are nothing less than the understanding of matter itself. To decipher a neutron star is to decipher the essence of the physical world, the way particles arrange, collapse, and resist in the face of crushing gravity. And so, humanity stands in a peculiar place, not at the end of the mystery, but near its thinning edge. The clues grow sharper, the contradictions fewer, the outlines clearer. Each new observation, each pulse, each ripple, each spectral line adds to a pattern that is beginning to emerge from the dark. There is a sense, whispered across observatories and laboratories, that a revelation is approaching. The stars, though silent, seem to be preparing to yield one of their oldest secrets, and when they do, the answer may redefine not only the life cycles of suns, but the very laws that underlie reality itself. In the silent void, where light itself struggles to escape the pull of dead suns, neutron stars endure as monuments of cosmic finality. They are what remain when a star's brilliance has been exhausted, when fusion can no longer stave off collapse. Yet in their silence, they are not empty. They are compressed echoes of suns, husks of unimaginable density, carrying within their cores not only the ashes of stellar fire, but the story of matter pushed beyond recognition. To look at a neutron star is to glimpse the death of a giant, frozen into permanence, a reminder that even the brightest lights must one day fade. And yet, they are more than tombstones in the sky. They are symbols of transformation, of endings that give way to beginnings. Within their depths, matter itself is forced to abandon its familiar structure. Protons and electrons fuse, neutrons crowd into each other, and in the process, identity dissolves. The particles that compose human bodies, mountains, oceans, and air particles that seem so foundational, so indivisible, lose their individuality. They become something else, something stranger. The rules that hold everyday matter together fail in this furnace of gravity, revealing a truth that matter is not fixed, but fragile. its form dependent on the pressures of its environment. If the essence of reality can change under such duress, what then is reality? A fixed stage, or a shifting illusion? For generations, scientists have wrestled with this paradox. From the first skeptics who doubted such stars could exist, to the young student who heard their radio pulses for the first time, to the modern teams that combine telescopes, detectors, and supercomputers across the globe, humanity has refused to look away. Each faint signal, each ripple in space-time, each glitch in a pulsar's rotation has been seized upon as a message from the unreachable. There is persistence in this chase, a refusal to let the darkness remain silent. It is as if the universe left these stars as puzzles, daring humanity to decipher them, knowing the pursuit itself would reshape how reality is understood. The irony is profound. Out of stellar death comes creation. When neutron stars collide, the violence is apocalyptic, but the legacy is beautiful. In those brief instances of unimaginable pressure and energy, heavy elements are born. Gold, platinum, uranium atoms forged not in the steady fires of ordinary stars, but in the cataclysmic embrace of collapsing giants. The ring exchanged in marriage, the circuitry powering human technologies, the treasures of history displayed in museums, all may trace their origins to a moment when two neutron stars merged in a distant galaxy, spilling their contents into space. Death becomes the author of beauty, destruction the midwife of creation. But beneath the science lingers a deeper question, one that cannot be resolved by instruments or equations. If matter itself breaks down here, if the very building blocks of existence unravel in the heart of a neutron star, what does that say about the nature of reality? Perhaps what seems solid, permanent, and indivisible in daily life is only a temporary arrangement. Perhaps existence itself is fluid, shaped by forces larger than comprehension, destined to transform when pressures grow too immense. The walls of reality may not be walls at all, but shifting boundaries waiting to be crossed. In this way, neutron stars are not the end of physics. They are the beginning of something new. They stand at the frontier where human knowledge falters, where equations grow unstable, where theories strain under weight they cannot bear. They are not just relics of stellar death, but harbingers of truths yet to be uncovered. In their silence, they whisper that the universe is deeper, stranger, and more fluid than imagination allows. And as long as their pulses continue, as long as their collisions ripple through space-time, humanity will listen, knowing that within those echoes lies not just the story of dying stars, but the next chapter in the story of reality itself. They linger in the night sky as paradoxes impossibly small, impossibly heavy, impossibly strange. Neutron stars are not merely objects. They are thresholds, places where the known dissolves into the unknown. They are reminders that the cosmos is not a completed story, but a manuscript still being written, one whose next chapter may already lie hidden in their depths. They sit at the limits of human imagination, waiting patiently, silently, as if daring anyone who gazes upon them to ask the forbidden question, what is matter when it has gone beyond matter? To reflect on them is to confront mortality itself. Just as stars die and collapse, so too does everything that lives. Suns burn out, civilizations fade, and even mountains erode into dust. Yet in neutron stars, death does not mean absence. Instead, it becomes transformation, a new state of being, one more alien and more enduring than what came before. Humanity has long searched for permanence, for something indestructible beneath the shifting surface of existence. But the universe offers a different answer. Even permanence is an illusion. Even the foundations of matter can be remade under pressure. What feels eternal is only a temporary arrangement. waiting for the gravity of time to reshape it into something else. And in that reshaping lies creation. The same stars that collapse into silent remnants can, when paired in binary orbits, collide to give birth to new elements. The shimmer of gold in a wedding ring, the gleam of platinum in a spacecraft's instruments, the heavy metals running through veins, all may trace their origins to neutron star collisions. The universe takes what is broken and remakes it, scattering treasure into galaxies. It is almost a cosmic parable. From violence comes beauty, from endings come beginnings. In this sense, neutron stars are not symbols of death, but of rebirth, proof that even destruction is woven into the grand cycle of creation. Still, the deepest lesson they hold is one of humility. For all the progress made, for all the equations, the detectors, the telescopes, the supercomputers, their interiors remain veiled. The equation of state is not solved. The secrets of quark matter, of hyperons, of exotic cores, are still locked away. Every breakthrough is matched by a deeper question, every answer by a darker mystery. Neutron stars remind humanity that science is not about reaching a final truth, but about forever pressing against the boundaries of ignorance. They show that the universe is larger than any single mind, larger even than the collective effort of centuries. To study them is to learn patience, to accept that mystery is not a failure of knowledge, but the very fuel of discovery. And so the pursuit continues. Scientists peer through radio arrays and space telescopes, trace gravitational waves across the cosmos, and run simulations on machines powerful enough to mimic stars. They search not only for the physics of neutron stars, but for what those stars imply about existence itself. In their silence, neutron stars are like mirrors, reflecting back the most difficult questions. Is reality stable, or is it fragile? Are there limits to knowledge, or only horizons that keep retreating? Is the universe ultimately knowable, or is it an infinite mystery? Perhaps that is why they fascinate so deeply. Not because they are distant or strange, but because they are intimate. They speak not only of the deaths of stars, but of the fate of matter itself, the same matter that forms human bodies, thoughts, and memories. In their cores, identity itself breaks down. What once were protons and electrons, what once carried charge and individuality, merge into a uniform ocean where difference ceases. If matter can lose its selfhood, what then of everything built from it? The philosophical weight is unavoidable. Neutron stars are not just the death of suns. They are metaphors for the fragility of all forms, all beings. Yet within that fragility lies hope. For if reality can change, if even the most fundamental things can be remade, then nothing is final. Not death, not collapse, not even the end of physics. Neutron stars may seem like boundaries, but they are also doorways. They are the places where the old rules crumble, where the cosmos hints that deeper laws exist beyond sight. They tell of a universe not finished but evolving, not closed but endlessly opening. In their silence, they do not speak of endings, but of the promise of beginnings yet to come. And perhaps, in that silence, humanity can find its own reflection. For just as neutron stars are the remnants of giants, compressed but enduring, so too is every mind a remnant of cosmic fire, born from stardust, shaped by time, capable of thought that reaches across galaxies. Humanity itself is proof that the universe creates wonder from collapse. To look upon a neutron star is not to see something foreign, but to glimpse the destiny written into matter itself, to transform, to endure, and to become something stranger than imagination allows. They exist at the crossroads of science and poetry, where mathematics falters and wonder takes hold. Neutron stars are not ordinary objects of astronomy, nor are they simply remnants of stellar death. They are crucibles where the very definition of matter dissolves, where identity itself is questioned. To speak of them is to confront the most haunting question science has ever dared to ask. What happens when the fabric of existence is pressed beyond recognition? These stars are not bright beacons to light the skies, but instead silent enigmas, flickering with pulses, whispering in radio waves, trembling space-time itself. They wait like ancient oracles, patient and unyielding, guardians of a truth humanity has not yet earned. Even the word star seems insufficient, for neutron stars betray every expectation bound into that word. A star suggests light, warmth, steady radiance. But here, light is trapped, twisted, and fractured. What remains is the carcass of brilliance, a shrunken ember of unimaginable weight. A neutron star may be no larger than a city, and yet it carries within it more mass than the sun itself. A single teaspoon of its substance would weigh billions of tons, a weight too vast to be comprehended, too alien to be placed against the familiar scales of Earth. Such comparisons, often repeated in textbooks and lectures, remain abstractions, for the human mind has no true grasp of 1 billion tons pressed into the space of a spoon. And yet this is not a metaphor, it is fact. Nature, in her indifference, has demonstrated that the impossible is not only possible, but real. In their silence, neutron stars remind us that the universe is not obliged to conform to human expectation. Physics, as it is known, unravels in their depths. The comforting hierarchies of protons, electrons, and neutrons, the scaffolding of reality, collapse into forms never encountered elsewhere. Some scientists imagine neutrons packed so tightly that they begin to dissolve into a sea of quarks, the most elemental building blocks known. Others imagine exotic condensates, particles that exist only under the tyranny of such pressures, ephemeral visitors summoned into being by gravity's demand. The truth remains unknown. Equations struggle, experiments cannot reproduce the conditions, and observation offers only distant hints. And so, neutron stars remain as puzzles, half glimpsed through clouds of theory, refusing to reveal their essence. The pursuit of that essence is not merely academic. It is not the idle curiosity of minds untethered from the world. It is something deeper, more human. To understand neutron stars is to understand matter itself. And matter is the foundation of everything, from the dust beneath one's feet to the thoughts passing silently through the mind. If matter changes form in the heart of these collapsed suns, then the question arises, what is matter, truly? Is it substance, permanent and indivisible, or is it only pattern, an arrangement that shifts under pressure? The answer matters, because it is the same matter that gives rise to human life. Neutron stars are not foreign curiosities. They are mirrors, showing reality under conditions too extreme for Earth, yet bound by the same laws that hold every breath and heartbeat together. For generations, humanity has wrestled with this mystery. When neutron stars were first proposed, they seemed absurd, too dense, too strange, too close to the edge of comprehension. They were dismissed by some as the fever dreams of theorists, phantoms of mathematics with no anchor in reality. And yet the universe proved otherwise. When Jocelyn Bell Bernal, a graduate student at Cambridge, discovered the first pulsar in 1967, the strange regular radio pulses arriving from the void, the reality of neutron stars could no longer be denied. What had once been speculative became undeniable, echoing across the cosmos in metronomic beats. Each pulse was a declaration. The impossible was real, and it was out there. But with confirmation came a deeper mystery. Pulsars revealed the existence of neutron stars, yet told nothing of their interiors. Their rhythm was steady, their signals clear, but the true nature of what lay beneath their surfaces remained cloaked. As decades passed, telescopes expanded the view. X-ray satellites uncovered neutron stars wrapped in magnetic fields so intense they could erase every hard drive, every credit card on Earth, even from halfway to the moon. Gravitational wave detectors captured the tremors of colliding neutron stars, revealing that their deaths scattered gold and platinum into space. The heavy elements adorning human bodies and technologies were born in such cataclysms. Yet even these revelations brought no clarity to the central riddle. How matter behaves in their cores remains one of the greatest unsolved questions of physics, and so humanity returns, again and again, to the silence at their heart. For inside them, matter is pressed to densities that cannot be mimicked in laboratories. The Large Hadron Collider, with all its power, cannot reach such conditions. Supercomputers struggle to model them. Equations collapse under the strain. They are laboratories of the extreme places where relativity and quantum mechanics meet and fail to agree. They are boundaries, reminding scientists that human theories, however elegant, are provisional. Somewhere, deep inside a neutron star, lies the point where current knowledge fractures. This is why neutron stars matter. Not only because they are strange, not only because they forge the metals of life and civilization, but because they stand as the test of physics itself. They are the crucibles where the two great pillars of science, general relativity and quantum mechanics, are forced to confront one another. Gravity presses inward, stronger than anywhere else, save the event horizon of a black hole. Quantum mechanics resists, invoking the degeneracy of neutrons, the last defense against collapse. Between them lies a fragile balance, a stalemate written into space-time. If one falters, the other takes over. If the neutrons resist, the star endures. If they fail, gravity wins, and a black hole is born. The philosophical implications are staggering. If neutron stars are balanced on the knife edge between matter and nothingness, between structure and singularity, then they are symbols of reality itself fragile, provisional, suspended between order and collapse. They remind humanity that existence is not inevitable, but precarious, the result of forces forever straining against one another. The cosmos, in its grandeur, is not fixed, but dynamic, always on the verge of transformation, and in their silence lies irony. These are corpses of stars, dead suns long past their brilliance, yet in their death they give life. They seed galaxies with gold and platinum. They guide astronomers to new theories. They illuminate the frontiers of physics. From their deaths arise beginnings. It is a cycle written not in myth, but in the stars themselves. Destruction begets creation. Collapse yields to transformation. Human culture has always sought metaphors for renewal in the rhythms of nature. The neutron star is the ultimate metaphor, the final truth written not in story but in space-time itself. Consider, for a moment, the human connection. The ring exchanged in marriage, symbol of union and permanence, may contain gold forged in the fire of colliding neutron stars. The circuitry of a spacecraft leaving Earth, probing other worlds, may rely on platinum atoms born in such collisions. The atoms of human bodies, carbon, nitrogen, oxygen, iron, were forged in ancient stellar furnaces. But the heaviest elements come from these violent deaths. To where gold is, to where the remnants of neutron stars. To live in a world enriched by heavy elements is to live in the legacy of their collisions. Humanity is bound to them, not metaphorically, but physically, materially. The connection is literal, undeniable, and profound. And yet, for all that intimacy, they remain remote. They lie hundreds or thousands of light years away, their signals faint, their cores forever hidden. Humanity listens to their pulses, traces their ripples in space-time. models their possible states in equations, but the stars themselves keep their secrets. This distance, both physical and conceptual, lends them their aura of mystery. They are close enough to shape human existence, but too far to fully know. They are companions in the cosmos, but silent ones, reminding humanity of the limits of knowledge. The question arises, will the mystery ever be solved? Will the interiors of neutron stars one day be known? Their matter described with precision, their equation of state pinned down. Perhaps, with each passing decade, science advances. The NICER experiment aboard the International Space Station maps neutron stars with increasing accuracy, measuring their size and shape. Gravitational wave detectors promise to capture more collisions, more signals from the depths of space-time. Supercomputers grow ever more powerful, able to simulate matter at higher densities. Progress is steady. The cracks in the mystery widen, but perhaps the answer is deeper still. Perhaps neutron stars are not mysteries to be solved, but reminders that reality itself is inexhaustible, that every answer will reveal only new questions, that every frontier reached will open onto another. In this sense, neutron stars are not the end of physics, but the beginning of it. They are invitations, urging humanity to keep asking, to keep listening, to keep pressing forward. The pursuit itself becomes the meaning, the endless unfolding of curiosity into the infinite night. And so, as the pulses continue, as the collisions scatter light and gold across galaxies, humanity watches. The stars do not answer, not directly, but their silence is not empty. It is filled with possibility, with wonder, with the reminder that reality is deeper than comprehension. They are corpses, and yet they are teachers. They are remnants, and yet they are beginnings. They are the graves of stars, and yet the wombs of creation. Perhaps one day the truth of their cause will be known. Perhaps the quark seas or exotic particles will be revealed, their mysteries unraveled. Or perhaps not. Perhaps they will always remain enigmas, forever whispering at the limits of thought. Either way, they will endure, pulsing in the darkness, patient and unyielding. They will remain as reminders that the universe is not only stranger than imagined, but stranger than can be imagined. And in that strangeness lies beauty. For in the end, neutron stars are not objects of despair, but of wonder. They tell a story that humanity cannot exhaust, a story written in silence and density, in collapse and rebirth. They are the cosmos reflecting on itself, the universe folding in upon its own matter, showing what lies beyond. To gaze upon them is to confront both mortality and eternity, both fragility and strength, both ending and beginning. The neutron star is a question written in space-time, and though the answer remains hidden, the pursuit of it reveals something greater that humanity is capable of asking, that out of dust and fire and collapse, consciousness has emerged, capable of wondering at the stars, of imagining what lies within them, of reaching beyond itself, and that, perhaps, is the final reflection. The neutron star is not only a mystery of the universe, it is a mirror of humanity's own mystery, fragile, fleeting, yet striving endlessly to understand.